Right now, something invisible is passing through the room around you. You cannot see it, you cannot hear it, you cannot feel it touch your skin, but it is there, moving through walls, crossing empty space, carrying voices, images, signals, and information without a wire. Behind all of this is one hidden truth. Empty space is not empty in the way we once imagined. Electric and magnetic fields can move through it, and those fields can carry energy. Take that truth away for 1 minute, and the modern world does not simply become quiet. It begins to collapse. Phones lose their voices. Satellites lose the earth. Radar goes blind. Messages stop moving. The world becomes disconnected, lost. Because the modern world is held together by something most people never think about: invisible waves moving through space. But for centuries, that idea sounded impossible. How could energy travel where there was no wire? How could electricity move through empty space? And how could light itself be connected to electricity and magnetism? The man who answered that question did not build the first radio. He did not launch a satellite. He never saw a mobile phone, a radar screen, or a wireless network. And yet, every one of them rests on the foundation he revealed. His name was James Clerk Maxwell, and he would reveal the invisible architecture beneath the modern world. He is not as famous as Newton, not as publicly remembered as Einstein, but without Maxwell, the wireless world has no foundation. This is the story of a discovery so deep, it changed what humanity believed space itself could do. But before Maxwell could reveal that hidden architecture, he had to answer one question. What actually moves through space when no wire is there?
Welcome to Architects of Electricity, where electricity meets history.
Before Maxwell entered the scene, scientists already knew strange things were happening. Electricity could attract, magnets could pull, a compass could point north. But then came a shock. In 1820, Hans Christian Ørsted noticed that when electric current flowed through a wire, a nearby compass needle moved. Electricity had disturbed magnetism. Soon after, André-Marie Ampère studied the connection more deeply. He showed that electric current could produce magnetic effects. Then Michael Faraday discovered the opposite effect. In 1831, he showed that a changing magnetic field could create electric current. This became electromagnetic induction, the principle behind generators. Motion could awaken electricity. One by one, the clues were growing. Electricity was real. Magnetism was real, and somehow they seemed to affect each other. But there was still no complete picture. Electricity was treated as one mystery, magnetism as another, light as something else entirely. Faraday believed the answer was hidden in space itself. He imagined invisible lines of force around magnets, around wires, around electric charges. To Faraday, space was not just empty background, it was active. It could carry direction, it could carry influence, it could connect one object to another without anything visible between them. But there was a problem. Faraday's vision was powerful, but it was not written in the language many scientists trusted most, mathematics. The clues were there, but scientists still could not see the structure that connected everything underneath. And without that structure, no one could truly explain how energy moved through empty space. That was the question Maxwell would have to face. Maxwell was not starting from nothing. Faraday had given science a new way to imagine the invisible world. Ampère had shown how current produced magnetism. Others had measured forces, built laws, and tested effects. But Maxwell saw something deeper. The world did not need another isolated clue. It needed a structure. So in 1855, Maxwell began the difficult work. He tried to take Faraday's invisible lines of force and turn them into equations, not just for one experiment, not just for one device, but for electricity, magnetism, and light together. For nearly 10 years, Maxwell worked to build a single theory behind it all, a theory of electromagnetic fields. But Maxwell's greatness was not that he invented every law from nothing. Gauss, Faraday, Ampère, and others had already built important parts of the structure, but the structure was incomplete. The pieces were there, but the system was not yet whole, and Maxwell saw the missing piece in one place: Ampère's law. That missing piece would change everything. Today, we remember Maxwell's theory through 4 famous equations, but Maxwell did not originally present them in the neat form students learn today. His theory was spread across many mathematical expressions. Later, Oliver Heaviside and others helped simplify the work into the 4 compact laws now known as Maxwell's equations. But the power was not in the number. It was in what those laws revealed. The first law said, electric charge creates an electric field. Where there is charge, there is electric force around it. The second law said, magnetic fields do not begin or end alone. In ordinary magnets, north and south always appear together. Magnetic field lines always close back on themselves. The third law came from Faraday. A changing magnetic field can create electricity. Move a magnet near a coil and current appears. This is the principle behind generators. The fourth law came from Ampère, but Maxwell completed it. Ampère's law explained how current made magnetism, but it failed at one of the simplest devices in electricity, a capacitor. Current seemed to enter one plate and leave from the other, but no charge actually crossed the gap. Maxwell saw the gap, not a gap in the circuit, a gap in the theory, and into that gap, he placed one new idea. A changing electric field could act like a current. Today, we call it displacement current. That single correction completed the loop. Faraday had shown that changing magnetism could create electricity. Maxwell now showed that changing electricity could create magnetism. And once electricity and magnetism could create each other, they no longer needed wires. They could move together through empty space as a wave. When Maxwell calculated the speed of this wave, the answer was astonishing. Roughly 300,000 kilometers per second, the speed of light. That was the moment the mystery changed. Electricity, magnetism, and light were not separate mysteries. They were one. Light itself was electromagnetic. And if light was an electromagnetic wave, then visible light might be only one small part of something larger. There could be other waves too. Waves the human eye could not see. Invisible waves moving through space. Maxwell had not built a radio. He had not sent a wireless message. He had not seen a satellite or a mobile phone. But his equations had opened the door to all of them. There was only one problem. Maxwell's waves existed in equations. Someone still had to prove they existed in the real world. But Maxwell did not live to see that proof. His waves existed in theory, on paper, in equations. Years after Maxwell's death, a German physicist named Heinrich Hertz decided to test the prediction. If Maxwell was right, then electromagnetic waves should not stay trapped inside mathematics. They should move through the air. They should cross empty space, and somehow they should be detectable. Hertz built a simple transmitter, not a radio set, not a communication machine, just 2 metal spheres with a tiny gap between them. When he applied a high voltage, a spark jumped across the gap. That spark was more than a flash of light. It was a sudden electrical disturbance. And according to Maxwell's theory, that disturbance should send an electromagnetic wave outward through the room. Then Hertz placed a second device nearby, a simple metal loop with a small break in it. No wire connected it to the first device. Nothing touched it. If Maxwell was wrong, nothing should happen. But when the first spark fired, a second, smaller spark appeared in the loop. That tiny spark was the answer. Something invisible had crossed the space between the 2 devices. It had left the transmitter, moved through the room, and reached the receiver. Maxwell's wave was no longer just an idea. It was real. Hertz pushed the experiment further. He showed that these waves could reflect. He showed that they could behave like light. And that mattered, because Maxwell had said light itself was electromagnetic. A spark had confirmed Maxwell's vision. Empty space could carry electromagnetic waves. And once that was proven, the wireless age was no longer a fantasy. It was only waiting for inventors to build it. But what began as a tiny spark in Hertz's laboratory would soon become the invisible nervous system of the modern world. Maxwell gave the world the theory. Hertz gave the world the proof. And together, they opened the door to the wireless age. Radio waves carried messages across oceans. Wireless telegraphy connected ships and cities. Radar learned to see through darkness. Microwaves helped power communication and sensing. X-rays opened a hidden view inside the human body. Satellites connected continents. Wireless networks filled the air around us. The electromagnetic spectrum was no longer just visible light. It became a new way to understand reality. Different wavelengths, different powers, different ways to see and connect the world. Maxwell's equations also changed how humanity sees the universe. The remains of exploded stars, the heat of distant dust clouds, the hidden surfaces of planets, the violent light of black holes and galaxies. The universe became visible in new languages, not just in color, but in waves. Maxwell showed that electricity, magnetism, and light were not separate mysteries. They were one connected reality. He did not live to see satellites, mobile phones, or wireless networks, but the invisible world they depend on was revealed by his equations. Because Maxwell answered the question that once seemed impossible. What moves through space when no wire is there? The answer was not a machine, not a cable, not a visible bridge. It was a wave, an electromagnetic wave.